Okay, in this video we're going to look at a couple of examples of the extreme value theorem for functions of two variables. So let's look at this theorem real quick. So let's say we've got a function f of xy of two variables. It's continuous on a closed and bounded set D, which is a subset of the plane. So in a previous setup video I talked about what it meant for a set to be closed and bounded in the plane, so I'll let you guys check that out if you need to. Then it attains an absolute maximum and minimum on this set D, and moreover we know where those maxes and mins happen, and they can only occur at critical points. So those are places where both partial derivatives equal 0 or on the boundary. Okay, so our first example we're going to look at is this function right here. F of xy is 4x squared y minus x squared y squared minus xy cubed, and then D is a closed triangular region with vertices, the origin 0, 6, and 6, 0. So before we get started, let's go ahead and draw a picture of that region. So notice it's all in the first quadrant, so that means that that's all I really need to draw. And then we have out here, let's say this is the point 6, 0. And then maybe up here, this is the point 0, 6. And down here, this is obviously the origin 0, 0. So the region that we've got going on has boundary given by these orange lines, and then interior given by that. Okay, so I'll put a D here to mean that that's our set. Okay, so those are the points that we're interested in. Okay, so let's first calculate our critical points, and then we'll worry about the boundary. So let's take this partial with respect to x of this function. Notice here that's going to give us 8xy minus 2xy squared minus y cubed. Okay, great. And then let's see, the partial with respect to y, so f sub y is going to give us 4x squared, and then minus 2x squared y, and then minus 3xy squared. Okay, good. And now what we want to do is set each of those equal to 0 and find some points that satisfy that system of equations. So let's set each of them equal to 0, and notice that this first equation we can factor a y out. So maybe let's number these. Let's number this one 1 and this one 2. So equation 1 we can factor a y out, and that's going to give us 8x minus 2xy minus y squared equals 0. Okay, good. But notice that that tells us that y equals 0 is one of the solutions, or that all of this part equals 0 is going to give us another solution. So let's notice if y equals 0 gives us a solution, what we also get as a point. Well, notice if y equals 0, if we plug that into f sub y, so let's denote that by this. So f sub y evaluated at y equals 0, so I'll do just x comma y there. Notice this part's going to 0 out, this part's going to 0 out. We're just going to be left with 4x squared equals 0, which tells us that x also equals 0. So that gives us a critical point of 0, 0. So we can go ahead and note that this point right here, 0, 0, is a critical point. Now notice that doesn't actually give us any more information in this case, because that's also a point on the boundary, and furthermore it's a point on the corner of the boundary, which means that it would have been an important point anyway. Okay, so now that means that we've taken care of the case when y equals 0, so we need to look at the case when all of this equals 0. So notice that's going to be 8x minus 2xy minus y squared equals 0. Okay, so let's see what we get for that. So for that, notice maybe we could have two ideas. We could either solve this for x or solve this for y using the quadratic formula. I think maybe it's easier to solve it for x. So that's going to give us 8x minus 2xy equals y squared, like that. And now notice that we could actually, let's stop right here. And notice that we can plug this into equation 2, and then we've reduced the order of the y squared term. So we haven't simplified it all the way, but we've reduced from needing a y squared to just needing a y, so maybe that'll help us. So just to reiterate, I'm going to take this equation that we've built for y squared, and I'm going to plug it into y squared up here. So let's maybe denote that by plugging this into equation 2, and let's see what we get. So we're going to get 4x squared minus 2x squared y minus 3x times the quantity 8x minus 2xy, and then all of this is going to be equal to 0. Okay, great. So now we can multiply that out, and let's see what we get when we multiply that out. So we'll get 4x squared minus 2x squared y minus 24x squared minus, let's see, that's 6x squared y equals 0. Okay, now we have some like terms that we can combine in this case. So we've got 4x squared minus 24x squared, and notice that should be a plus. So that's going to give us minus 20x squared from combining those two. And then we have minus 2x squared y plus 6x squared y. So that's going to give us plus 4x squared y. So that's what we get for that. But now notice we can factor an x squared out of that. We can actually maybe factor a 4x squared out of that. Maybe that's the best thing to do. We can take a 4x squared out, and notice that is going to give us minus 5 plus y equals 0. Okay? So notice that's going to give us the critical point x equals 0. But notice if x equals 0, that means y equals 0 from this right here. Okay, good. Or it's going to give us the critical point y equals 5. Okay, so now let's see what happens if y equals 5. So let's take this value of y equals 5 and plug it in here and see what we get. So that's going to give us 8x minus 10x, great, equals 25. So that gives us minus 2x equals 25, which tells us that x equals minus 25 over 2. Okay, good. But now let's notice where that is in the plane. So y equals 5 is about right here. But then x equals minus 25 over 2 is way out here. So we don't actually need to worry about that. Okay, so now let's put a summary up here of what we found via all these calculations. So this means there are no critical points in the interior of D. And I'll just put D like that. There might be some on the boundary, but we'll get those another way. Okay, so I'll clean up the board, and then we'll look on the on the boundary of D for some more important points. Okay, so now that we've looked for critical points on the interior of D and we didn't find any, we found this one at this corner, but we would have gotten that one anyway. We want to look for critical points on the boundary. So notice the boundary is going to be broken up into 3 pieces. I'll call them curve 1, curve 2, and curve 3. And notice each of those will satisfy different equations. So notice on curve 1, we have that y is always equal to 0 because it's the x-axis. And then we have that x is trending between 0 and 6. So that's going to turn this into a Calculus 1 type problem on curve 1. Okay, so let's see what we get in that case. So in this case, f of x, y collapses to f of x comma 0, which I'll just denote by f of x. So I'm going to plug y equals 0 into this whole thing, but notice I get this is equal to 0. Okay, good, but notice that tells us that f prime of x equals 0 for all of these points also. So what we can take away from that is that every point along this curve is a critical point, and in fact we know that f of x equals 0 on this whole boundary curve. So we'll actually use that later, but we will just keep that in the back of our mind for now. So now that we're going to look at what's going on in curve 2. So notice curve 2 is described as a line with slope of -1 and y-intercept of 6. So that means we can write curve 2 with the equation minus x plus 6. And notice x is again on the closed interval 0 to 6. Okay, so now let's see what happens to f of x here. So f of x comma y, which is -x plus 6 in this case, will be gained by plugging in -x plus 6 in everywhere we see y. So in other words, it's 4x squared y minus x, it's 4x squared minus 6 plus x minus x squared minus x plus 6 squared, and then finally minus x plus 6 cubed. And then it's fairly elementary to multiply that out and combine all like terms. So this is going to be equal to minus 10x cubed plus 96x squared, and then finally minus 216x. Okay, great. And now notice we can apply Calculus 1 on that to take the derivative. So that's going to give us minus 30x squared plus, so that's going to be 192 x minus 216, set that equal to 0 and solve for the roots. And in fact, you're going to have to use the quadratic formula in this case. So we'll get x equals, so I'll skip the details, it's 2 over 5 times the quantity 8 plus or minus the square root of 19. Okay, good. And you can check that both of those are within the region where x is between 0 and 6. So those are both going to give us important points. So I'll go ahead and calculate the y value for those points. We can get by just doing 6 minus these x values, and then we'll keep that in our list of important points up here. Okay, so I'll clean up this part of the board in order to put those important points, and then we'll also finally focus on this curve C3. Okay, so far the important points we have are given by our corners 0, 0, 0, 6 and 6, 0, which obviously come from those being on really the end points of the boundary, if you will. And then we found these two important points, which are given by 2/5, 8 plus the square root of 19, comma 2/5, 7 minus the square root of 19, and then a similar one with some minus signs and plus signs switched. And notice if we graph all of those points, again, we've got one on each corner, and then we also have one about right there and one about right there, and those correspond to these two. Okay, good. Now the last thing we need to do is look at what's happening on curve C3. But it's actually very, very similar to what's happening on curve C1, and let's see that. So on curve C3, we know that x is always 0 and that y is running between 0 and 6. Okay, but notice that f of y is going to collapse just to 0 on this whole curve, which means the derivative is 0, which means this whole part of the boundary is a critical point where we know that value is f of 0. Okay, good. So let's just reiterate. We know this entire boundary is a critical point and f is 0 here. This entire part of the boundary is a critical point and f is 0 here. And then we have two more critical points here and here given by these two numbers. And so those are obviously going to be where our max will occur, or our minimum if we get negative numbers plugged into there, but we'll just have to see. Okay, so I'll clean up the board and then we'll summarize what we found. Okay, so let's look at our summary. So we had our important points x comma 0, where x runs from 0 to 6. That's right here. So f was always 0 on that x-axis. And then 0 comma y, where y runs from 0 to 6. So that's right here. And f was always 0 there as well. And then we had these two important points which happened on our boundary, which we calculated before. So if you plug those into the function, which you can get an exact answer. But here I just gave an approximate answer. So this gives you negative 141, and this one gives you positive 70. So that means we get a minimum here and we get a maximum here. Okay, good. So I'm going to clean up the board and then we're going to look at another example like this. Okay, so now we're ready for another example. Let's say in this example we've got the function f of xy is 2x cubed plus y to the fourth, and our region D is given by all ordered pairs xy, where x squared plus y squared is less than or equal to 1. So to get an idea for what that looks like, we know that x squared plus y squared equals 1 is everything on the unit circle. So let's denote that by writing this here. So notice all of the points here are given by x squared plus y squared equals 1. And then everything inside is given by x squared plus y squared is strictly less than 1. So putting that together, you get something called the unit disk. Okay. Good. So now that we've got our picture, let's go ahead and find our critical points. In other words, the places where the partial with respect to x and the partial with respect to y are simultaneously 0. So in this case, we've got a pretty simple function. The partial with respect to x is given by 6x squared. Set that equal to 0. We get x equals 0. The partial with respect to y is 4y cubed. Set that equal to 0. We get y equals 0. Okay, great. So that gives us a critical point right there at the origin, 0, 0. So when we make our list later, notice we're going to have some important points. We already know that 0, 0 is going to be on that list of important points. Okay, so now let's look on the boundary. So notice on the boundary we have x squared plus y squared equals 1. So in order to calculate what's happening on the boundary. So notice we have two choices here. We could solve this for x and plug it into the function, or we could solve this for y and plug it into the function. Or we could do something a little bit more clever and solve this for y squared, get that that is 1 minus x squared, and then square that to give us y to the fourth equals 1 minus x squared squared, which is going to be x to the fourth minus 2x squared plus 1. And now notice, since y only shows up in our function as y to the fourth, that's actually good enough for expressing this function on the boundary. So that means on the boundary we have this thing collapses to a function of x, and that function of x is given by 2x cubed plus x to the fourth minus 2x squared plus 1. Okay, great. And notice this bit came from just this formula, and then this bit right here came from our y to the fourth power. Okay, fantastic. Now let's go ahead and take the derivative. So if we take the derivative with respect to x, that's going to give us 6x plus 4x cubed minus 4x. Sorry, that should be 6x squared. Good. Now notice we can factor a 2x out of that. So if we factor a 2x out of that and then maybe rearrange it so that we're in decreasing order, we're going to get 2x squared plus 3x minus 2, and we want to set that equal to 0. Okay, so notice first of all, we get a critical point when x equals 0. But now notice if x equals 0, plugging that up here, we get y squared equals 1, which tells us that the point 0, 1 and 0, -1 are also important points. So let's go ahead and put those, here and here. So those are also important points. Okay, great. And now we need to solve for this polynomial in the middle to see what's going on there. And notice that thing factors nicely, so that's going to be equal to 2x, and then 2x times x. So let's see how this will work. I think we need a +2 here and a -1 there. So notice that's going to give us 2x squared plus 4x minus x minus 2. So that's what we get. Okay, great. So now notice here, this is going to give us x equals -2, which we don't need because that is outside of our region. And then this guy right here is going to give us x equals half. Great. But now notice if x equals 1/2, we can plug that in up here. And notice that's going to give us the following. 1/4 plus y squared equals 1, which tells us that y squared equals 3/4, which tells us that we have the points 1/2 and then the square root of 3/2 and 1/2 negative the square root of 3/2. Okay, good. So notice those are going to be points like right about there and there. Okay, good. So now that we have our 1, 2, 3, 4, 5 important points, we can check their status. So I'll clean up the board and then we'll do that. Okay, so now we're ready. We had these important points which we figured out earlier. So we've got the origin, that's the only interior point that's interesting. And then we have all these points on the boundary. So notice those are points on the unit circle. 0, 1, 0, -1, half, root 3/2, and then half negative root 3/2. So those look like values of sine and cosine, which obviously makes sense because here we're on the unit circle. Okay, great. And now notice that if you plug those in, you get 0, 1, 1, 13/16, and 13/16. And so notice 0 is obviously the minimum in this case, and then 1 is a maximum, and that occurs in 2 spots. And this 13/16 is kind of a neither point. It might be a local maximum or a local minimum, but that's hard to figure out without doing the second derivative test. Okay, that's a good place to end this video.